Let's put all the elements of binomial probability together to solve our problem. So from parts 1 and 2, we have a coin, a special coin, whose probability of heads is 2/3. It's a tricky coin, it's weighted, or something. And the probability of tails, heads complement, is 1 minus 2/3. That's how we got 1/3. And we're going to go ahead and flip it 10 times, and we are looking for the probability of exactly 3 heads. If we define heads as success, we could say x equals the number of successes, and this is sometimes how it's written in binomial probability language, in textbooks and stuff like that. We can just write probability 3 heads also. I just want to make sure I put that in front of folks because that's another way to write it. So, in part 1 we learned that we're going to end up seeing the probability of heads 3 times in a sequence of probabilities all multiplied together. That sequence is 10 parts long. So we're going to have the probability of heads of success to the power of 3, because somewhere in that sequence the 2/3 is going to appear 3 times. And then we're going to have the probability of failure the other 7 times. So we know that this is going to be part of our calculation. The only thing we needed to add is, from part 1 going into part 2, is we needed an expression that would give us how many times we need to multiply that. The expression here, the combinatoric expression, tells us how many different ways there are to have a sequence of 2/3 sprinkled among 10 locations where they might be found. In other words, all the patterns or orders that we could have those heads fall into. Heads, heads, tails, heads, tails, tails, and so on. You remember how that goes. That's from part 1 mainly. So that's the combinatoric expression. So if we just work this problem now, we're going to have the answer. We have 10 choose 3. That's going to be 10 factorial over 3 factorial, 10 minus 3 factorial. So that is 10 times 9 times 8 times 7 factorial. We have 3 factorial, which is 3 times 2 times 1, times 7 factorial. Let's go ahead and cancel that. We're left with the 3 and the 2 on the bottom. I'm going to cancel the 3 on the bottom and divide 9 by 3. I'm going to cancel the 2 on the bottom and divide 8 by 2 and be left with 4. And so what we have is, for the combinatoric expression, we saw this at the end of the second video, I guess. That's going to be 10 times 12. So we have 120. Okay, so we know 10 choose 3 is equal to 120. I made some space here. I erased and made some space. And 2/3 to the 3rd power is 0. This is an approximation, 0.296296. 1/3 to the 7th power is, I have it on good authority, I'm looking past the camera, let's make it 000457. So what we're going to need to do to get our answer is multiply those together, which I did already, and I got, make sure you're getting the same answer as I am. As a matter of fact, you may want to pause the video right now. Just pause it for a second, make sure you get the same thing I do. But what I got was 162,576,84. So that's a lot of digits. Obviously, that's probably too many digits for purpose. You could trim that, truncate it, or round it or something. Anyway, that's what I got. So that's the answer to the question that we've been working on through these 3 videos. Let's do something a little bit, I guess, more important than one specific problem. You'll remember the way that I wrote out the problem a few moments ago, I wrote this because it makes sense to us. And we've been building up to looking at it this way. There's a multiplication between each one of those elements. The generic form of this formula will usually be n choose, I like R, many textbooks use X. Let's use X this time. N choose X times P to the X times 1 minus P to the n minus x. Now let's take a look at this and see that it agrees completely with what we've been working with and what makes sense to us intuitively. We have n being the number of trials and x being the number of successes. That's 10 choose 3 in the formula above. We have the probability of success to the power of how many successes we're expecting. This number and that number always agree. And then we're multiplying it by the complement of success, that's failure, 1 minus p to the power of n minus x. In other words, out of n trials, there's x successes, and that means that n minus x failures. And that's why it's written that way. If you're a student working these problems for the first time, it's really just a matter, once you get the idea of how it works and the logic behind it, it's really just a matter of chugging it out, working it out. But mistakes are common, and they usually come from people sort of losing track of what they're doing. So I suggest that you write yourself a key and then just plug in. You would write something like n equals the number of trials. You might write to yourself x equals successes, and so on. P equals the probability of success. Make a key first, and then you can plug things in, and then it'll be very easy. Do you remember, I'm going to pose a question here. Maybe I'll do a follow-up to this video too. Not part of the official series, but just a follow-up, because I'm going to ask you a question right now. And the last, teaser that I gave out, a question, I think it might have been too easy. I think a lot of people got it. So I'm going to try something a little bit tougher. You remember that from part 2 of this video that 10 choose 3 and 10 choose 10 minus 3, meaning 10 choose 7, ought to be the same number, right? Okay. So what I want to know is this. If we consider heads to be the success, and we're calculating the probability of 3 successes in 10 flips, we had this construction. I want to know, with the same coin, the probability of 7 failures. I want to know how you set it up. I want to see you calculate it in exactly the same way, and I want you to see what the probability is of 7 failures and whether or not it should or ought to be the same number. So let's try that. I'm going to throw that out, and we'll do a follow-up video with the answer to that, some exercises, and some constraints on binomial probability.